What's up, people? This is Prachuja Viswas and welcome to Atomic Structure Lectures. In the last lecture, we studied about the J.J. Thomson atomic model, and today we will study about the Rutherford model of atom. Before we study about this model of atom, it is important to revise the J.J. Thomson model of atom and also certain radioactive properties of an atom. First of all, if we discuss about the J.J. Thomson model of atom and we revise it once again, it is called the watermelon model of atom also because it consisting of a positive sphere, and inside this positive sphere are small electrons which are donated by green. This is called the J.J. Thomson model of atom but was not taken into consideration due to various types of irregularities in this. So we had to move to another model of atom, and which was given by scientists called Ernest Rutherford of Britain. It first to understand that what he actually used was radioactivity. In the later half of the 19th century, different kind of rays were starting to be discovered. Wilhelm Röntgen in 1895 showed that when an electron strikes a material, in a cathode ray tube, it produces rays which can cause fluorescence in fluorescent materials placed outside of the cathode ray tubes. Since Röntgen did not know the nature of these radiations, he called them X-rays. So this is the X-rays that were used in the Millikan experiment in order to derive the nature of the charge. It was noticed that the X-rays are produced effectively when electrons strike the dense metal anode called targets. These are not deflected by electric or magnetic fields and have a very high penetrating power through the matter. These rays are thus used for the study of interior objects like the same that are used for studying our bones, in case we have a fracture or any type of breakage in our bones. Henry Becquerel, who lived from 1852 to 908, observed that there were certain elements which emit radiation on their own, and thus named the phenomena radioactivity, and the elements were known as radioactive elements. This field was thus developed by many scientists like the famous Marie Curie, who won the Nobel Prize twice, first for physics and then for chemistry, Pierre Curie, her husband, Ernest Rutherford himself, and Frederick Soddy. It was observed that there were three kinds of rays that were majorly took place in radioactivity. There were the alpha, beta, and the gamma rays. Rutherford found that the alpha rays consisted of high energy particles carrying 2 units of positive charge. Thus, if we have an alpha ray here, this has a positive charge of 2 plus, or we can say of a 2e. It also had an atomic mass of 4u, which means the mass of that alpha particle was 4 times the mass of a single proton. He concluded that the alpha particles were helium nuclei, as when alpha particle combined with 2 electrons yielded helium gas. Then it's very difficult to understand the concept of nuclei, but when we go into the Rutherford model of atom, we will understand the concept of nuclei. You can say that this thing here is a group of protons and neutrons in which it contains of 2 protons and 2 neutrons. Therefore, we have 4 objects like this which consists of 2 protons and 2 neutrons. Beta rays were negatively charged particles and were similar to electrons. The gamma rays were high energy radiations like X-rays and are neutral in nature and do not consist of any particles. As regarding penetrating power, alpha particles have the least penetrating power, and beta rays followed that was 100 times that of the alpha ray particle, and the gamma rays having 1000 times that of the alpha ray particle. Now let's move on with the Rutherford nuclear model of atom. We always know that if a model of atom was taken into consideration, this was done using a certain type of experiment, and this experiment is given here. This is the Rutherford Goldfoil experiment, but it was actually called the Geiger and Martin experiment. The Geiger and Martin were actually 2 students of Ernest Rutherford who used to teach chemistry and used to teach radioactivity. Now what they did was they used some setup like this, in which there was a lead box. This here is the lead box, and in this lead box there came a radioactive element or a radioactive source. From this radioactive source, a beam of alpha particles came out of it, And using a small window or a small hole here, these radioactive particles were sent through it and they're told to hit a gold foil which is very, very thin, about an, let's say, um size of 0.1 meter or even smaller than that, say 100 nanometer of gold metal. So this gold foil consisted of only a width of around 2 to 3 atoms. Now this thin gold foil had a circular fluorescent zinc sulfide screen around it. So whenever an alpha particle struck the screen, a tiny flash of light was produced at the point. And this screen or the fluorescent light was called a detector. Now when the alpha particles were told to hit on that gold foil, a certain number of assumptions were taken place. Now if we consider the J.J. Thomson model of atom, which is a circle of positive charge with like this electrons embedded in it, then it was told that if alpha particles are very heavily charged and this is not so heavily positively charged, then two things can happen. First, it might go exactly 180 degree back due to electrostatic repulsion, or secondly, it would hit the atom and would stay past, like it would just deflect a little or so much that, or third, it could get absorbed, right? But the results of the scattering experiment were quite unexpected. According to the Thomas model of atom, the mass of each gold atom in the foil should have been spread evenly, and alpha particles would have enough energy to pass directly through it, such a uniform distribution of mass. Right. But what actually happened was the observation as they are noted here. Most of the alpha particles travel through the foil undeflected. This was given very easily by the Thomson model of atom, but it was then proved that when the Thomson model of atom, they would have been gone around a deflection of 1 to 2 degrees, but in this they went without any deflection, say around 0 degrees. So it was interpreted that the atom is mostly empty space. The second observation that was done was some alpha particles were deflected by small angles, say around 15 to 20 degrees. 15 to 20 degrees. So this was also very absurd according to the J.J. Thomson model of atom, because 15 to 20 degrees were not that of deflection that was like should have been observed or was assumed from J.J. Thomson model of atom. So the interpretation was that there is a small center in the atom outside which there is a blank space. Now when the rays came from this direction and was very close to the nucleus, they deflect at an angle say around 20 degrees or 15 degrees. So this was the explanation that was given. Now, so interpretation thus were given that the nucleus is positively charged, as is the alpha particle. Now, it was also seen that there were certain particles that went through a 180 degree deflection. That is, occasionally an alpha particle travels back from the foil. Thus, it was proved that the nucleus carries most of the atom's mass. What it was thought about is that if there is a nucleus like this, which is having a very high density of mass, then it must have a very high density of protons. Therefore, what was happening here was that if the alpha particle came in this direction, then it has to go back because of the electrostatic repulsion. That would happen in the J.J. Thomson model of atom, but in the J.J. Thomson model of atom, the mass was evenly described, so that the case of this being happening was very less. Therefore, at last, this kind of model of atom was taken into consideration. There is this thing, the nucleus, which consists of most of the mass of the atom. The most of the mass of the atom is concentrated in a small nucleus containing of the protons and the neutrons. The positively charged is also concentrated in the middle. Therefore, if we now try to explain the alpha particle, let's say that there is an alpha particle here and it is moving in this direction here. So what will happen here is, because the nucleus has a high charge density, high positive charge density, it will repel the alpha particle and will come back in this direction. Similarly, if there is another alpha particle which is moving in this direction, very close to the atom, then there is some repulsion in this direction too. Therefore, it will move by this angle, around say angle of 20 degrees. Now similarly, if an atom is moving very far away from the nucleus, and thus the repulsion is not so much that it will deflect it from a much angle. Therefore, even if it get deflected, it will get deflected by a very small angle of 1 degree or 0.5 degrees. So this we can say is undeflected. So the result of a nucleus coming into picture was considered to be very right. Now considering that of the electrons, we can say that the nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called the orbits. Thus, the Rutherford model of atom resembles the solar system in which the nucleus plays the role of the sun and the electron play the role of the planet. This model of atom is called the atomic planetary model of atom. This electron and the nucleus are together attracted or repelled by the electrostatic force of attraction. So what is happening here is, if they consider this electron here, then there is an attraction in this direction, but there is also a repulsion in this direction. Thus, in all, the forces combine and this remains in a good position. So this was the Rutherford model of atom. If we look at it in the better picture rather than slanting rings, the model of atom looks something like this. There are a nucleus in between which consists of the proton and the neutrons, and there are orbits around it in which the electrons revolve. So this is the Rutherford model of atom. But there is a slight problem in this Rutherford model of atom. The Rutherford model of atom assumed that the electrons move around in circular paths along the orbits. But in the circular paths along the orbits, we can say that if these forces do not balance each other, because the electrons are revolving around in the orbit, but in case it does not maintain the forces, then the electron must fall into the nucleus, but that does not happen. Also, later when we study in the next the Bohr's model of atom, it would be seen that when any charged particle accelerates, it releases energy. And if the electron loses energy, then the electron orbit should become less and less, but that does not happen in this case. In this case, the electron remains in its position, and that is the Rutherford model of atom.